Okay, today we want to be able to take a look at what's called a compound event probability. And in order to do that, there's some terms that we need to know and understand. First, the set of all possible outcomes in a probability experiment, that's called the sample space. Sample space is the set of all possible outcomes of an event. Organized lists, tables, and tree diagrams can be used to represent the sample space. Another way to find the total number of possible outcomes is to use the fundamental counting principle. And the fundamental counting principle works this way. It says an event M has M possible outcomes. An event N has N possible outcomes. The total number of outcomes of event M followed by event N is M times N. Now, what does that mean in regular, regular language? That means something like this: flipping a coin, right? If you flip a coin, there are two possible outcomes, right? When you flip a coin, you have heads and you have tails. So there's two possible outcomes for the coin flip. If you're rolling a number cube, right, six-sided number cube, there are six possible outcomes. So let's say this is event M, right? That's event M. This is event N. And what the fundamental counting principle says, if you have two possible outcomes for an event, and then you have six possible outcomes for another event, flipping a coin, rolling a number cube, to find the number of possible outcomes that the event would be for flipping the coin followed by rolling the number cube, you simply multiply the number of outcomes. So if you have two possible outcomes for one event and six possible outcomes for another event, you have 12 possible outcomes for the two events. All right, rather simple. A compound event consists of two or more events, right? And that's when we're going to use that counting principles, or we're going to use the, find the sample space. As with a single event, the probability of a compound event is the ratio of the number of favorable outcomes to the number of possible outcomes. Okay? Let's take a look at some problems. Here it says we want to find the sample space. And remember, the sample space is the set of all of the possible outcomes of an event. You randomly choose a crust and style of pizza. Find the sample space. How many different pizzas are possible? Okay, well, if we're looking for the number of possible outcomes of the event of thin crust and stuffed crust and the different styles, right? If we're looking for the number of possible outcomes, we would take two possible outcomes. Oops, let me do that again. There are two possible outcomes for crust. There are four possible outcomes for style. So there would be a total of 8 possible outcomes, or 8 possible combinations of the of the pizza. But we're looking for the sample space, and a sample space would be a list of all of those outcomes, right? Not how many there are, but the list of those outcomes. And in order to make that list, we create the sample space. And one of the methods that we use, and the method I like to use the most, is the tree diagram, and it works this way. Right? So first we're going to start off with the crust. And what are the different types of crusts that we have? We have thin crusts and we have stuffed crusts. Then we have the style, right? And what kind of styles do we have? We have Hawaiian, Mexican, pepperoni, and veggie. So we would make our tree diagram this way. If I have a thin crust pizza, right, there are 4 possible styles of thin crust pizza. We could have a thin crust Hawaiian, a thin crust Mexican, a thin crust pepperoni, and a thin crust veggie. If I have a stuffed crust pizza, there are 4 possible styles of stuffed crust. I can have an Hawaiian stuffed crust, a Mexican stuffed crust, a pepperoni stuffed crust, or a veggie stuffed crust. The sample space allows us to take the information from the tree diagram and create our sample space. And the sample space is the list of all the possible outcomes. So what are those outcomes? Well, the first outcome, when I read my tree diagram, I read it this way. I could have a thin crust Hawaiian, So that's going to be a T and an H. That's a thin crust Hawaiian. I could have a thin crust Mexican. So that's going to be a T and an M. I could have a T with a P. I could have a T with a V. If I have a stuffed crust, I could have a stuffed crust Hawaiian. So that's going to be an S with an H. S with an M. Stuffed crust Mexican. S with a P and an S with a V. So here's my sample space of my 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes. And we knew about our 8 possible outcomes because of our counting principle. 2 possible outcomes for crust, 4 possible outcomes for style, 2 times 4, 8 possible outcomes. That's how the counting principle works. But the sample space shows us what those specific outcomes are. So there are 8 different pizza combinations, right? 8 different pizza combinations. All right. And that's how we use the tree diagram to create the sample space. Okay? Let's try another one. Next problem says, what if the pizza shop adds a deep dish crust? Find the sample space. How many possible outcomes, or how many pizzas are there possible? Well, if we add a deep dish, right, we'll call that a D, right? A deep dish. That means instead of 2 times 4, we would then have, right? We would then have, boop, 3 times 4, right? So we know that there are going to be 12 possible outcomes down here, right? So down here for this next problem, there are going to be 12 possible outcomes, right? But we want to know what those outcomes are. So we're going to set up our tree diagram the same way. First, we're going to start with the crust, but there are 3 possible crusts. We're going to add the deep dish, but then we still have the thin crust and we still have the stuffed, right? And then we have the styles, right? With our styles, there are 4 possible styles for each, right? H, M, P, and V. 4 possible styles here. H, M, P, and V. And 4 possible styles here. H, M, P, and V. Our sample space is going to show a list of those 12 possible outcomes. So we would have D with H, right? D with H here. It's going to be D with H, D with M. We have D with P, D with V. Then we have T with H, T with M, T with P, T with V. And then we'll have S with H, S with M, S with P, and S with V. So we could see our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We could see our 12 possible outcomes in our sample space, right? So there are 12 different pizza combinations, right? 12 different pizza combinations when we add the deep dish as an option for the crust. Okay, all right, let's move on. Find the total number of possible outcomes. Find the total number of possible outcomes of rolling a number cube and flipping a coin. Now we're just looking for the total possible outcomes. All right. So here, method 1, they use a table, and the table helps us kind of make a list here, right? When we flip a coin, we could have heads or tails. Right. Here's heads. Right. Here's tails. And when we roll the number cube, we could roll a 1, a 2, a 3, a 4, a 5, or a 6. So here we have 1 with a head, meaning if I flip the coin and get heads, right, I could have heads with a 1, heads with a 2, heads with a 3, heads with a 4, heads with a 5, heads with a 6. If I flip the coin and get tails, I could have tails with a 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5, tails with a 6. Right, so that's just one possible way to see the 12 possible outcomes, right? If I have 2 outcomes for the coin flip and 6 possible outcomes for the number cube, right, 2 times 6 gives me 12 possible outcomes. I see it here. And that's what we're being asked down here, to use the counting principle, right? So for the coin flips, right, coin flips, there are two possible outcomes. For the cube, right, there are 6 possible outcomes. So when we multiply using the counting principle, 2 times 6, right, we would have our 12 possible outcomes. So you can make a table to show the sample space, and that's what we see here in that top part. We see the sample space, but we could also use the counting principle if we're just being asked how many possible outcomes are there. All right, let's move on. We want to find the probability of what's called a compound event. And a compound event is the probability of one thing happening after another, or one thing or two things happening together. Here it says in example 2, what's the probability of rolling a number greater than 4 and flipping tails? So we have a compound event, 2 different events. Well, let's talk about event 1. The probability of rolling a number greater than 4 would be what? Well, we have a 5 and a 6 on a number cube that are greater than 4, so 2 out of the 6 outcomes would be possible for the probability of a number greater than 4. Well, what about the probability of tails? Right, probability of tails, there's one tail out of the 2 possible outcomes. So we want to know the probability of a number greater than 4 and tails. Right? That's what we're being asked here. So we want to multiply these 2 probabilities. So we take 2 out of 6, which is the probability of rolling a number greater than 4. We want to multiply that by 1/2, which is the probability of getting tails. Right? We divide these out, 1 and 1, and we wind up with 1 out of 6 would be the probability of rolling rolling a number greater than 4 and flipping tails. All right, let's continue. How many different outfits can you make from t-shirts, jeans, and shoes in the closet? Well, once again, we want to use the counting principle here. And let's start with our t-shirts. How many shirts are there? We have 1, 2, 3, 4, 5, 6, 7 shirts. Right? How many jeans do we have? It looks like if we count carefully, we have 1, 2, 3, 4 jeans. And how many sneakers or shoes do we have? We have 1 pair, 2 pairs, 3 pairs of sneakers in the closet. Well, the counting principle says that the number of outfits is going to be equal to 7 times 4 times 3. Right? So we multiply the number of possible outfits, or the number of possibilities for each category, and we wind up with 84 different outfits. Right? 84 different outfits. All right? Let's continue. All right, couple more questions here. Find the total number of possible outcomes of spinning the spinner and choosing a number 1 to 5. Well, let's take a look at the spinner to the right. There are 1, 2, 3, 4 different possible outcomes for the spinner. So for question 2, for the spinner, right, we have spinner outcomes, right, we have 4. And then choosing a number 1 to 5, right, the 1 to 5 outcomes, right, there are 5 of those, right? You could choose a 1, a 2, a 3, a 4, or 5. So, if we want to know the total number of possible outcomes of spinning a spinner and choosing a number 1 to 5, it would be 4 times 5, which would be 20 possible outcomes. Right? Possible outcomes. All right, for problem number 2. Let's look at problem 3. How many different outfits can you make from 4 t-shirts, 5 pairs of jeans, and 5 shoes? Well, using the fundamental counting principle, we're just going to multiply 4 times 5, right, which is 20. 20 times 5, there'd be 100 different outcomes. Right, 100 possible outcomes. right? Just using that counting principle, right? So you see that the math isn't hard. You just have to know how to use that counting principle correctly, all right? Let's get into some more problems. The three students chosen to represent Mr. Baldrick's class in a school assembly are shown. So we have Adriana, Adrian, Carlos, and Greg. All three of them need to sit in a row on the stage. Use a list to find the sample space for the different ways they could sit in a row. Okay, well, let's try to make a list here. Well, if Adrian is first, you could have Greg second and Carlos third, or if Adrian is first, you could have Carlos second and Greg third. If Carlos is first, you could have Adrian second and Greg third, or if Carlos is first, you could have Greg second and Adrian third. All right, and then if we have Greg first, you could have Adrian second and Carlos third, or if Greg is first, you'd have Carlos second and Adrian third. So use the list to create the sample space. Well, here's our sample space, right? There are 6 different ways, right? 6 ways, different ways that they could sit in a row. Right, next example. It says a car purchased in blue, silver, red, or purple can be purchased. It also comes as a convertible or hardtop. Use a table or tree diagram to find the sample space for the different styles in which the car can be purchased. Well, if we make a table, right, it would look like this. We could have blue convertible, a blue hardtop. Silver with a convertible or silver hardtop. Red convertible, red hardtop. Purple convertible, purple hardtop. If we made the use the tree diagram to create the sample space, it would look like that. All right, so that's just an example of the 2 different ways. We've talked about tables, making tables, and we've talked about the tree diagrams, right, to create the sample space. But the goal is to come up with a sample space, right, the list of all of the possible outcomes of an event. All right, let's continue. You flip 3 nickels. What's the probability of flipping 2 heads and 1 tail? Let's see. Well, coin flip number 1, you could flip a head or tails with the first coin. If that first coin lands on heads, that second coin could be heads or tails. If that first coin lands on tails, that second coin could be heads or tails. If the first coin lands on heads and the second coin lands on heads, that last coin could be heads or tails. If the first coin lands on heads and the second coin lands on tails, that last coin could be heads or tails. All right, we're going to make our list that way, heads and tails, and finish it down here, heads and tails. The sample space we'll put over here. Right, the sample space is going to look like this. Right, we could have with our 3 coins, heads, heads, and heads. Right, so that's H, H, and H. Heads, heads, tails, heads, heads, tails. We could have heads, tails, heads, heads, tails, heads, heads, tails, tails, heads, tails, tails. We could have tails, heads, heads, tails, heads, heads, tails, heads, tails, tails, heads, tails, 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 heads, tails, tails, heads, and finally tails, 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 tails. So what is the probability of flipping 2 heads and 1 tail? Well, now that we have our sample space, we want to look for 2 heads and 1 tail. Right, so we have 2 heads and 1 tail here, 2 heads and 1 tail here, and I have 2 heads and 1 tail here, and I think that's it. Right? So out of our 8 possible outcomes, right, there are 3 of the 8 possible outcomes. Right? So the probability of 2 heads and 1 tail, right, is equal to our 3/8. All right. All right. Let's take a look at some of these problems down here. 4, 5, 6, and 7. See if we can get those done pretty quickly. In example 2, what's the probability of rolling at most 4 and flipping heads? Well, at most 4, that would be rolling a 1, 2, 3, or 4. So for problem 4, there are 4 out of the 6 possible outcomes of rolling a number cube are at most 4. And then flipping heads would be 1 out of 2. So we'd have to multiply. When we multiply, let's see, divide out. That's 1, that's 2. We wind up with 2 over 6, which simplifies to 1/3 for question 4. Right, question 5. In example 5, what's the probability of flipping at least 2 tails? When we go back up here, at least 2 tails. When we see, let's see, change colors here, at least 2 tails. Here's 1, at least 2 tails. Here's 2, here's 3, right? Looks like there's 4, right, where there are at least 2 tails. So for problem 5, we would have 4 out of the 8 possible outcomes, which simplifies to 1/2 for question number 5. Question 6. Let's see what it says. You roll 2 number cubes. What's the probability of rolling double 3s? Well, the probability of rolling a 3 on the first number cube would be 1 out of 6. The probability of rolling a 3 with the second number cube would also be 1 out of 6. The probability that these two events, creating a compound event, happen together would be 1 out of 6 times 1 out of 6, which would be 1 out of 36 would be the probability of that compound event. Question 7. In example 1, what's the probability of choosing a stuffed crust Hawaiian pizza? Well, we're going to have to go back to question 1. Right, that's way back here, question 1. A stuffed crust Hawaiian pizza. Well, here's a stuffed crust Hawaiian, right? And it looks like there's just one of those 8 outcomes where we have the stuffed crust Hawaiian pizza, right? We have 8 possible outcomes, and only one is stuffed Hawaiian, right? So let's go back here. Right, gotta go ahead. I think we're one more. Yep, so the stuffed Hawaiian, looks like that's gonna be 1 out of 8. All right, we continue. The table shows the sandwich choices for a picnic. Find the sample space using a list, table, or tree diagram for a sandwich consisting of 1 type of meat and 1 type of bread. All right, well, let's start with the meat. You could have ham or you could have turkey. All right, and then you have the bread. And for bread, we could have rye, sourdough or white, rye, sourdough or white, and same thing here, rye, sourdough or white. So my sample space is going to look something like this, right? We could have H with R, H with S, H with W, T with R, T with S, T with W. So it looks like our sample space consists of 6 different ways of having the sandwich and the bread. All right, let's continue. All right, let's see. Suppose you toss a quarter, dime, and nickel. Find the sample space. What's the probability of getting 3 tails? Make a tree diagram. Let's start with our quarter. Quarter could land on heads or tails. With our dime, dime could be heads or tails, or heads or tails here. And then we have our nickel, all right? That could be heads or tails, heads or tails, heads or tails for the nickel, heads or tails. So when our sample space, right, our sample space, that's going to be heads, 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 tails, heads, tails, heads, heads, tails, tails, what do we got? Tails, heads, heads, tails, heads, tails, 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 tails. Oops, no, I missed something. Tails, tails, heads first. Oops. And then tails, tails, tails. So we should have 1, 2, 3, 4, 5, 6, 7, 8. What's the probability of getting 3 tails? Here's my 3 tails. So the probability of tails, tails, and tails, that's simply 1 out of 8, right? And we could have used the counting principle for that, right? Because you have a 1 out of 2 probability for the first tail, 1 out of 2 possibility for the second tail, 1 out of 2 possibility for the third tail. So you'd multiply 1 out of 2 times 1 out of 2 times 1 out of 2, and that would also give you 1 out of 8, right? So we could use that counting principle for those types of problems. All right, let's go down here. The animal shelter has both male and female Labrador retrievers in yellow, brown, or black. There's an equal number of each kind. What's the probability of choosing a female yellow lab retriever? Show your work in the sample space. Okay, well, let's talk about the dog and what are the possibilities for the dog. Well, you could have a male dog, female dog. And then we have the color. Right, the color, we could have, what, 3 options? Yellow, brown, and black. All right, 3 options here: yellow, brown, and black. So when we do our sample space, right, take a look at our sample space. We could have a male yellow, we could have a male, we got brown, we could have male black, and that's okay. Or we could have a female yellow, female brown, or female black. What's the probability of choosing a female yellow? Here's my female yellow. So the probability of female in yellow, that's going to be equal to 1 out of the 6 possible outcomes for the female yellow. All right, let's continue here. To win a carnival prize, you need to choose one of 3 doors labeled 1 through 3. Then you need to choose a red, yellow, or blue box behind each door. What's the probability that the prize is in the blue or yellow box behind door 2? Well, the sample space is already created for you, right? Using a list, door 1, door 2, door 3. So we have 2 possible winners here out of the 1, 2, 3, 4, 5, 6, 7, 8, 9. So the probability of 2 with blue or yellow is equal to 2 nines, right? And that's just reading from our organized list on the in our sample space. Okay. All right. Let's finish this up here. Some tougher problems. 3 counters are labeled according to the table at the right. Toss the 3 counters. If exactly 2 counters match, player 1 scores a point. Otherwise, player 2 scores a point. Find the probability that each player scores a point. All right, well, we need to create some sample space here. All right, so we're throwing 3 counters. All right, so let's start with counter number 1. Counter number 1, right, we could have red or we could have blue for counter number 1. If counter number 1 is red, counter number 2, we have red with yellow. If counter number 1 was blue, counter number 2 could be red with yellow. Counter 3 can be blue or yellow, right? So that's going to be blue with yellow here. It's going to be blue with yellow here. It's going to be blue with yellow here. And that's going to be blue with yellow here, right? And we're just getting that information right, from our table here. Counter 1, we had red and blue, so that's why we have R and B. Counter 2, we have red and yellow, that's why we have R with Y, R with Y. In counter 3, we have blue with yellow, that's why we have B with Y, B with Y, B with Y, B with Y. So the sample space, right, we're going to have R, R, B, R, R, Y, R, Y, B, R, Y, Y, B, R, what's that, B, B, R, Y, B, R, Y, B, Y, B, and B, Y, Y. So what does it say? If exactly two counters match, player 1 scores a point. So where does player 1 win? Right? So winner 1, right? Winner 1. We have two counters match here. Two counters match here. No. Two counters match here. Two counters match here, right? Blue with blue. No here. Two counters match here. Two counters match here. So winner 1, the probability of 1 wins is equal to 6 out of 8, or 75%. That means then probability 2 wins, right? 2 wins any other way. So 2 wins here, right? Oh, change colors, right? 2 wins here and 2 wins here. So probability 2 wins is only 2 out of 8, or 25%. All right? All right, let's scroll down and see what else we got here. Refer to exercise 7. Do the two players both have an equal chance of winning? Right? No. Right? Because player 1 is 75% chance of winning. And player 2, right, P2, is going to be a 25% chance. All right, and then our last question, Caitlin wants to determine the probability of guessing correctly on 2 true-false questions on her history test. She draws the tree diagram below using C for correct and I for incorrect. Find her mistake. All right, well, on question 1, she can get correct or incorrect. Question 2, if she gets question 1 correct, she could get question 2 correct or incorrect. If she gets question 1 incorrect, question 2 she could get correct or incorrect. Let's create the sample space. C with C, C with I with C. Uh-oh. Right, there's a mistake here. Right, that should be I with C. And then we have I and I. So there's the mistake, and we just corrected it. All right. Been a lot with this lesson. Just remember, when we're finding probability of compound events, we could use the counting principle, multiplying the probabilities of the individual events to find the probability of the compound event. And we can also use our sample space. And sample space is the list of all of the possible outcomes of an event. And we can use a organized list or a table or a tree diagram to create that sample space. All right, good luck.